Hello, good morning, everyone, and welcome to our final day, the last day of AstroSprint Enterprise. And we'll start off with a talk by Najam. Najam, sir, on N-body sims with N-body 6, right? So over to Najam. Yeah.
Morning to all, and we'll continue with what we left with. In fact, we had two sessions on N-body simulations. It was first one was done by me, and then yesterday Sandeep did a very comprehensive session on N-bodies again, and there were certain things which we had looked into, which I will try to again show to reiterate certain point. But the basic purpose of today's talk is to actually download a software and show how you can install it and start using it. Okay, and I will in particular be doing it with N-body 6, which is a good software for doing simulations of clusters, star clusters. And what are the things which we can study is what I'll try to indicate. Sandeep will be talking on gadget, which are good for galaxy interactions and various things. Okay, so let me share the screen. Yeah. So yesterday we looked into this relaxation time, and basically what is relaxation time? It's a time interval after which the irregular forces arising from chance encounters will have changed the orbit of the star so much, such that to such an extent that the actual orbit can no longer be described, even approximately, by the regular orbit, right? So this is the relaxation time. Like we had seen earlier, we have, when we are looking at an N-body system, we have yeah, so like we had seen in the previous talk, if you have a system of N bodies, you know their masses and their positions, and on any particular mass object or a star, whatever you treat it as, the force which is acting on, say, the ith body is a resultant of external forces, then irregular forces and regular forces. Regular, right? We had seen what these were. And when we take this F external as 0, then we call the system isolated. Isolated. That is, it is only the internal forces within which of this system is what is acting on it, right? So you have regular forces is a cumulative force due to the potential of all this, and which sets uh, the object into certain regular orbit. Okay, and when it comes in contact very close to some other one, then it can get kicked off and it can take some other path. And the time after which the effect of this chance encounter, this irregular force dies down, that is called the relaxation time. Okay, so there are certain terminologies which are used in dynamics of star clusters. One is this relaxation time. One is another one is crossing time, dynamical friction, and these are the terms which come across while we are dealing with forces. And these are very well discussed in Binney and Merrifield, Binney and Tremaine books. So, where is this now? Yeah. So when you can look at the two body interaction, if you have mass m2 and m1 is going in a certain orbit, initially it's pretty far. Say if it's a parabolic one, then it comes from infinity and goes off to infinity. And as it starts coming closer, it starts influencing this. So in the absence of this m2, this body would have moved along the straight line, but due to the presence of this, it takes a certain trajectory, and the deviation by which it moves is what we are interested in, right? And these are the equations of motion which we had mentioned in the previous one. This is the equation of relative motion, and the solutions of which come as conic sections. Depending on what this E is, if E is 0, you get a circular orbit. If E is between 0 and 1, less than 1, you get parabolic, eccentric orbit, and 1 gets parabolic, and greater than 1 gives you hyperbolic orbits, right? And we can calculate this E, the eccentricity, in terms of the velocity of the object and this impact parameter, D, right? And obviously it depends on the masses, and so you have m1 and m2 in the denominator, g square, and this would give you the eccentricity. And the angle by which sigma by which it gets kicked off is given by g m1 plus m2 by dv square, right? So a little bit of classical mechanics can give you. And this shows that the delta v by v is sine psi by 2. Okay, so having a taking a relook at relaxation time, we can define it in two more ways. We can also say relaxation, the time of relaxation is the time after which, on account of the cumulative effect of stellar encounters, a star will have deviated by an angle 90 degrees from its original direction, right? Or a restatement of that is the time of relaxation is the time after which the total change in energy of a star due to irregular forces becomes of the same order of magnitude as its initial kinetic energy, right? So this gives you an idea into what we are talking about by relaxation time. And then when we were discussing the mass segregation in star clusters, we had said that if you look at the age of the cluster and calculate the relaxation time and compare them, so if the relaxation time is larger than the age of the cluster and it already shows mass segregation, then we would attribute that to primordial segregation, right? Otherwise, if it is relaxed and the age of the cluster is beyond the age of the relaxation time, then we can think, or we may also imply that this probably has happened due to relaxation, due to the dynamical effect, right? And like we had seen earlier, we had seen these two. Um, relaxation time. Yeah. Relaxation Time due to Beanie and Merrifield. And Sandeep mentioned yesterday, this concept was introduced by Chandrasekhar, and this is the value he gives for relaxation time. But this has been treated very well in the Galaxy Dynamics book by Beanie and Merrifield. Okay, and then this is the crossing time. There's the radius of the stellar system, and this is the velocity dispersion, and the time, the distance it takes for it to go across, yeah, is called the crossing time. So I think we are pretty much convinced as to why do we need simulations, what is the importance of studying simulations. This has been discussed um, by both Sandeep and me. There are various things which we uh, get a deeper understanding into stellar systems. For example, we have this famous Hubble tuning fork diagram, which is a morphological arrangement of galaxies from ellipticals to spirals. So, though Hubble had arranged them just on the basis of the morphologies, but people had started believing that this is also the evolutionary scheme, right? So, people started feeling that ellipticals, they started feeling that it's from ellipticals to spirals. So, due to gravity, the mass, the stars fall into a spherical symmetric object. And if the galaxy is rotating fast, then it starts bulging at the equatorial plane and it goes from E0 to E7. And then a disk appears. And due to some, right, so you get the lenticulars. And then due to some perturbations, the spiral features develop. So people started believing that it is this is not just a morphological but rather an evolutionary scheme too. But then it is realized today that this is not quite correct, and this was done essentially when people looked at simulations, right? And we have seen simulations done by Toomre and Toomre, where they showed that you can have two spiral galaxies which can interact and merge to form ellipticals. So this not only explains how certain galaxies look so weird and have all kinds of, like the one on the right side is the mice. This is called the mice because it looks like two mice interacting. So people earlier couldn't understand what these objects were and why these galaxies looked so. Secondly, these simulations have thrown light not only that they have explained how these tidal features are created, how morphology of galaxies change in time, but the simulations can also uh, explain how star formation rates can change in certain galaxies, uh, and uh, and why certain galaxies have uh, starburst galaxies while others show us a constant formation and so on, of star formation and so on, right? So why the star forming rates? And other than that, we also saw that these probably can also answer us this question about mass segregation. Like, why do you see more massive stars at the center and no mass stars outside? Secondly, we can this leads us to understanding why clusters dissolve, why do they disrupt and finally merge with the field stars, though they are all born in clusters, right? So now I will stop with this at the moment, and I will take you to uh, take you to a code which is very good for simulating start. And essentially is the N body. Yeah. Can you do one thing? Make me, yeah. So there is this N body 6. Just a minute.
Yeah.
Yeah. So can you see my screen?
Sir, we could see your browser.
Yeah.
Yeah, that's it. That's it.
I wanted to be far from this screen. Yeah. Okay. So there is you
Sir, we cannot hear you.
yeah, say R set and body. Can you hear?
Yes, sir, we can hear you.
Now can you hear? Hello.
Yes, sir, volume is bit low.
Yeah. Can you hear me?
Sir, yeah, we can hear, but the volume is too low.
Can you hear fine?
Still low, ma'am.
Okay. Okay. Yeah, yes, I can. Yeah, so go to Swear Arset's Institute of Astronomy. Hello. Hello. Yeah. Okay, so go to Swear Arset's um, Institute of, and here you will see
Your voice is breaking.
this N body page, right? So my research into numerical simulation of many body and body gravitation interactions spans over 40 years, right? So Swear Arset is a great person. He is the father of N body simulations, and he was the first one to share his code with others. He wrote excellent code for simulating stellar, and he made it public. And since then, many others have followed suit and they share the code. So if you look at this, there's this N body 1, N body 2, 3, 4, so on. And it is not that N body 1 is for one body simulations and 2, but this is how it has evolved. So N body 6 is what you should take. So there is a README file, and better get used to reading these documents and manuals. And so always you have a README file, README 1 and there's a README 2. So if you go there, it tells you certain details, and suppose I click it open, it would, yeah, so it is saving it somewhere, and we can read it. Yeah. What I'm interested in is also this nbody6.tar.gz. Okay, so you click that and download it. I'll save it at some, say I'll save it on my desktop. There's too much there. Yeah, I'll save it in my downloads. And you see the download is complete. Okay. So can you see my, yeah, I can see that. So we go to the location, downloads, and you will see that you have a nbody6 tar.gz. Okay. So what I will do is I'll make, say, a directory mkdir, and I'll make it this work directory where we are going to do this, or I'll call this session 1. Okay, and I will move my nbody6.tar.gz into this session 1, and I will get into here, and we are having this. Okay, let me clear it up. Sorry. Yeah, so here we have our tar.gz file. So you can unzip it. I do it in two parts, nbody tar.gz, and I have a tar file now, and I untar it by tar extract, verify, and force using nbody tar. Okay. So now you will notice that it has created. This was the tar file. If you want to save space, you can get rid of this rm nbody tar. I'll get rid of it. I don't need it anymore, and it has created these uh, subdirectories: AR chain, AR int, block, chain, docs, GPU2, N chain, and N code. So this N code, as it kind of hints, it contains the code. If I get into this, I change directly to N code. I've noticed that there are a host of Fortran files. There are a lot of programs: adjust.f, ss.f, bin.f, and so on and so forth. There are many, and each one, if you want to see, for example, um, nbody his.f. Okay, I'll open this, the main one, nbody6.f. Yeah, nbody6.f. So if you use um, whichever editor you require, you are familiar with, nbody6.f, you will see that it has, this is a program. Okay, very well documented, uh, and it gives you the whole thing. Program and what it includes this, and so on, right? So there are thousands of, this is the um, main program, and this calls all other programs which do other things. We call adjust, call start, and so on and so forth, right? So the beauty is you see the whole uh, source code is given, and you can make changes to that. Like for example, there is this orbit.m. Yeah. So this obviously it handles something to do with the orbits, right? So they have stability and various things. Okay. Yeah. I'll come out from this directory for a minute, and I will go to this docs directory, and here you will see that it has a lot of documents. Okay. So for example, you have man6.pdf. It is a manual for running this. You have the text one also, but you have a PDF, right? Similarly, you have nbody2ps. Yeah, for the nbody2, nbody5, they are all documents which are there. You have these readme files, readme. So you can go into these readme, and this directory contains several useful files for running nbody6. nbody6.txt is a text file which lists all the routines in this, right? So it tells you the whole story, and so make it a habit to uh, read it before you start. And it says here to compile, type make nbody6 in directory encode. First check F77 or F95, right? So initially for the people who are doing these things for the first time, it looks very cryptic and strange what they are trying to say. But the more you handle this open source code and software, you'll get more and more comfortable with it, and you'll realize what it's saying. So basically, if you see what it says is, in directory encode, you type make nbody6. Okay. But he says first check F77 or F95. Okay. So what what they what he means what he means is we should go into this n code. Sorry. I'll have to come out of this and go into n code. Right? See, now we are inside uh, home Najam download session 1 and code, right? And this was where I had taken you first. So here he says to run the command make nbody 6. But before doing that, he wants to check, he wants you to check what is the compiler you are using. Whether you are using F77, right? So when I ran F77, it said no input file, compilation error. What it indicates is I have F77 already installed on my system. Okay. Similarly, there is G Fortran. I think I have both the compilers here. And again, it says no input files. Okay. So that means both are there. We don't need both. We need only one of it. This G Fortran is a new one. So what we need to do is we have to go into the make file. Make file. There is a make file there, and in this you have to see which is the compiler which is being used to compile the whole thing. For example, here it says fc equal to F77, hash ld equal to F77. So
So if we were to use F77 compiler, I should uncomment these two. But instead I want to use this G Fortran. That's why I have uncommented these two, right? Yeah. I mean, this got done by default. I didn't do it, but it came when I downloaded and blew up the whole thing. The make file which is sitting inside already has this uncommented G Fortran. But in case for my system, I know I don't have G Fortran, but I have F77. Then I would put comment here, and uh, I would uncomment uncomment this one, right? So actually, I will be happy with what we have. Yeah, this is fine. So all is fine. Now what I need to do is I will run this make n body 6, and right. So there is that make file which tells the compiler how to compile, how to link them, and how to create the executable file. So it is going through all this, and you just have to sit, wait and watch. And sometimes it gives warnings which are okay, but if there are errors coming in, then you have to make a check on that and probably correct those for that, right? So see, this is something which is done by all programmers. When you have a program which is pretty big, you break up your program into smaller files, and then when you compile it, you link them up. You compile and link them up, right? So that make file which we had, I will show you what it looks like while it is compiling behind. Okay, it has, yeah, before we could do that, it's already come, and it has already come, and it has created n body 6, right? It didn't give me any errors, nothing like that. Everything got done fast. And when I look into that directory again, this time if you can notice, earlier we only had FFF, Zare.f, orbit.f, but now you have these O files, object files, right? So it compiled, created object files, linked them up, and so on. So now we don't need these object files. We just need the executable one which it has created. And this is where it is sitting. It has created a n body 6. This is the executable file. Okay. So so that I don't mess up my this encode directory, I will I will do one thing. I will come out, either come out or directly. In session 1, I will make directory called say run. Okay. And I will copy from this encode n body 6 n body 6. I want to copy it to this run directory. Okay, so if I get into my run now, uh, n body 6 should be sitting here, right? I've copied it because one is sitting in n code. You don't need it there anymore, but there's no harm. It doesn't take much space, so you can keep it there, because if it just gets corrupt for some reason, you can always pull that out. So you have this n body 6 here. Now I need something more. I need an input file. Okay. So for that input file, if you recall, I'll open another terminal. I'll open another terminal and I will go into my downloads and session 1 and docs, right? So in these docs, where there were a lot of different files, there is one input file. Okay, not just this one, but in bins and there are various. Okay, we'll see. Look at them later. As of now, look at this input file, right? And I should. What is this input file? If I see the contents of this input file, uh, you see it has some stuff written there. One, some 10,500, one, right? So this is the basic input file which is required, the sample input file which is required to run your N-body 6. So what I need to do is I will copy copy this input file into which directory where my run run is. Okay, so cd, I'll come out and go into run, and what I see is I have N-body 6 and I have input file. So if you recall, when we were looking at the readme file, there was one which said how to compile it, and further down in the same one, it also told you how to run it. So for example, yeah, where is that file? I'll just show you. So I can even locate it this way, download session 1, and in docs there was this readme file. See, it has all these N-body files, various N-body 6 PDF, manual PDF, all these things are very important files which you need to use. And where is it? One is this manual 6. Anyway, yeah, okay, here it is, readme file. So if in this readme file, it had first shown us how to compile this thing, and now uh, you see it said make N-body 6 unit, and then here it says to run type N-body 6 input output ampersand, right? So basically we have to say dot slash N-body 6, and I'm redirecting the content of input file by using the less than sign. I have an option, it is not necessary. I will run it without putting it in the output directory, or I'll run it without. I'll do it both ways. When I do it and body and run it, you see that it is running the whole thing. Okay, so it is running the simulation, but yeah, and you'll see a few new files get created. Say, I'm running it somewhere here, right? Yeah, so note the following floating point exception are signaling this is invalid flag divided by 0, whatever the normal, right? So it has stopped and it has created some more files. See, in our directory, we just had nbody 6 and input file. Now it has created something else. Escape fort.1 fort2, right? And if you want to see what these files are, I can run this file command and say escape, file escape, and it says it's an ASCII text file, right? So I can safely see this escape file, and it is giving me some numbers, 43.6. So basically, when you go further and see, you will see which are the stars which are escaping. They get written in this escaping file. So each star gets numbered and it gets written. Okay. The same thing I will run it. I will remove these three files which got created. Yeah. And I will rerun this. I'll rerun nbody 6 and I will output it into some out, whatever name you give. So instead of what is appearing on the screen and we are unable to handle it, if you say you redirect the output into this out file, and very often you use the ampersand so that it happens in the background. It is running behind, and the prompt is available for me to do other things, and you can see that as it is running, it is creating the same file behind, right? Okay, so it's stopped now, and if I see this out file, uh, I will see all the details. And this output file, as you notice, the same thing was coming on the screen. Now it is getting written properly into a file, and it is showing me some details. N500, Npix1, Ncrypt 25, Nran 10,000, NNB max 70, Nrun and delta T critical QE, right? Energy, change in energy, and all this. Then you have options which are 1 to 50, and you have some numbers 1 1 0 0 1 0. To understand what is happening, it's better we look at the input file. Yeah, so initially the whole thing looks pretty formidable, but once you get understand what is happening, then you can use it meaningfully, and you don't run it blindly as though in a black box. So you see the out file and the input file. There are certain things which are common, right? At least the second line, you look at this 500, 25, 10,071. So this n which is there in the input file, this n is the number of stars which we are running the simulation with. So n is 500. If you wanted to run it with 10,000 or 20,000 or 30 or 3 or whatever, you change it here. So in this case, the input sample file which was there, it has 500. N fix is 1. Critical time is 25. And then random number generation, you give a seed. And these are the things. And then if you see the options 1, 2, 3 to 50, these options are listed here. See, these are 1, 2, 3, 4, these are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then another 10 and another 10. So from here to here, there are 50. So there are these 50 options. Okay. And yeah, so this itself has explained to us a lot of things which we have to know. And further down, as you see, at different time steps, it is calculating various things, R min, E tau, enclosed, G min, all this, right? The tidal parameters, total mass, and what are the time steps at this time 0 n equal to 500, number of binaries 27, and right? CPU time elapsed. So, and then it keeps showing you various things. What is the kinetic energy? What is the right? So all these are being dumped here till the time uh, the calculation got halted, and it is because we reached the time 24. We have taken t in the here we are taking time for the simulation to be 25, right? So it did the 24 and then it came out of it because it probably was going beyond the. Okay. Now the question is, what are all these numbers standing for, right? This is the tricky part, and these are the things which you spend a lot of time trying to understand, and these are very well documented in our docs in the manual. If you if you look at the if you look at the manual 6, this is a manual which tells you what the whole thing is about, right? This is the user manual framework that has been extensively used and tested, uh, developed in 1992. Uh, the code is mainly integrated to run for laptops and workstations and etc. About the regularization which have been used, the Hermite method which has been used, how it got incorporated and all those things. And the code structure, how is the code arranged, and the whole code consists of 55,000 lines including comments and layout spaces. It's written in Fortran and F76 compliant and compiled with G77, and all these details are there. And it tells you what this common block, common 6.h is, and so on. And once, so getting started, so it explains to you how to uncompress, download and uncompress it, and when you untar it, what are the things you get, and what are all the subdirectories for, and then uh, this is a crucial document which you need to understand and work. Okay. Now here it gives you what are the input parameters. So it says that kj. Yeah, I'm just skipping through to tell you. Yeah. So see, for example, if kz5 is 1, 2, or 4, then it is it. If you put the kz5 in the input file, where is the input file? Yeah, in the input file, these are the KZ options 1, 2, 4, 5. So if I put a 1 here, then it creates one cluster which is like a plumber uh, plumber model, right? Similarly, you can change that. You can change that to you can change that to 2 or to 4, and it gives you uh, two orbiting clusters or a massive bound unbound binary, right? Similarly, you have uh, option hash 20. 20th one, you can choose what kind of distribution, whether you want salpeter mass distribution or you need Krupa or Tia or Gilmore and so on. Yeah. So by adjusting those parameters 1 to 50, you can trigger on tidal forces, you can trigger off tidal forces, you can uh, set the percentage of binaries in it, you can choose different initial mass distribution functions and so on and so forth. So you have to understand what each one stands for by toggling it 1 or 0. Like this one is to T start, it starts with 1. And suppose you want to rerun the whole thing, then you start from where you have stopped. So you change it to 2 and you put the other input parameter and so on. Okay, so uh, this code is extremely good for simulating star clusters, and it's much easier to simulate globular clusters because you can very well describe their distribution as uh, in plumber model or whichever distribution because they're theoretically symmetric ones. But open clusters are a bit trickier to do. But then as you proceed, if you are interested, then we can go and we can discuss how to construct different distributions. So basically, we, we require a system to create a model where you distribute masses to particles in a certain way. Either you give all of them same mass or you give them different masses. You can say how many should sit within a certain central region, how should the density fall, right? So you can write short programs to do it, or many programs are available to create that. In fact, this Embody 6 itself has a lot of features. Then this Embody 6 also has features where you can trigger star formation on and off. You can trigger on and off tidal forces because of the gravity. In fact, we have given some more sample files in the same doc file. This in-bins is another sample file, input template for 400 primordial binaries and 600 single particles, right? So this 400 and 600, this is the number which we have, right? Similarly, there's another sample file which is given here, which tells you, yeah, this is in GR. This is input file for GR captured gravitational radiation, right? So this N-body 6 has evolved tremendously. It's a good, uh, uh, very good program to simulate star clusters. And if we have been toying with this for a long time, so if you are interested, we can help you running of this. Okay, so with this, I will stop telling you to download this thing. If you're having problems installing, sometimes your make may not run, so you'll have to install the make facility. If you are in Linux, then you say sudo apt-get install make, and then the make would start running. If your Fortran is not there, then when you say G Fortran or F77, it will say program not found. You install it using apt-get install F77 or whatever, and install it. Okay. And then go through these manual pages. They're all these embodied 6 PDFs. Yeah, it describes all the routines perfectly. In fact, we have spent a lot of time in tidying this up. And if somebody is interested, we can jump start them for getting into actually uh, running meaningful simulation with with tiny forces switched on, with the stellar evolution switched on, or other things. Okay, so let me stop for now, and let me take questions.
Sir, how do we do the visualization of the simulation?
Yeah. If there are questions, you can.
Sir, how do we do the visualization of the simulation? Hello, sir. Can you hear me?
Chat. Okay, there are some. Could you hear me, all of you?
Sir, now it is much better. But we were able to hear you, but not that clearly.
That I've put it up. Yeah, it's unreal.
Hello, can somebody tell us all what's fine? Any questions? Any questions?
बढ़ा दिया है.
Yes, sir. How do we do the visualization?
Hello. Are
Hello,
there any
sir.
questions? Put it on the chat window. Yeah.
Okay.
Are there any questions or?
Yeah, they are.
Yeah. Okay, fine. So, you just.
Okay, so if there are no questions, then let's welcome Shushan.
Sir,